Welcome to the deep dive.
Hello.
Today we're plunging into quite a stack of sources. We've got lecture excerpts, briefing documents.
All from a data and design class.
Right, and the focus is really foundational for anyone creating digitally CAD software development.
Yeah, our mission here basically is to pull out the core ideas, maybe some, surprising bits, and the practical insights from all this material.
It's really about understanding how those design processes you might know,
hmm
the thinking, the steps, how they can actually be, well, structured and packaged into these powerful software systems.
And it's not just about lines of code, is it?
Not at all. These sources, they really frame it as understanding computation itself as a system.
The system for design, yeah, but also for research.
Exactly. So get ready for maybe a few aha moments about what's really going on under the hood of the tools you might use every day.
It's definitely a look deep beneath the surface, isn't it? At the architecture that makes it all tick.
So let's start with the big picture that these sources lay out. There's this central idea, right? That the ultimate goal of studying algorithms or data processing
Both vector and raster.
and figuring out how to codify your design thinking.
Hmm.
It isn't just like theoretical knowledge.
The end game, they argue, is to package all of that capability into actual working software.
Like a CAD tool for design, for research.
And what really struck me is the weight they put on this. The lecturer calls it a software revolution.
Yeah, of the 21st century.
Yeah.
And even puts it in the same league as AI, which is wow.
It is a huge claim.
Hmm.
But, when you break it down, the fundamental difference software brings.
It's that it's executable, right?
Right.
And distributable.
Exactly. Knowledge in a book is static, requires interpretation,
But knowledge in software, you can just run it, use it immediately.
and share it globally, instantly. It kind of bypasses the old ways of sharing knowledge.
The sources use that phrase, standing on the shoulders of giants.
Right. Because even simple software can contain this immense hidden complexity, all this accumulated knowledge.
Just waiting to be executed by anyone.
It definitely shifts how you think about design knowledge.
Okay, but then the sources draw this really sharp distinction. And it might be surprising, especially if you come from, say, a more traditional architecture or design background.
Absolutely. They contrast the development process in traditional design, like schematic design,
Yeah.
with software development.
And in traditional design, you often have that rapid iteration, right? Trial and error.
And let's be honest, sometimes that last-minute push, the cramming, the source mentions that cramming is possible there.
You can pull an all-nighter to finish the drawing.
You can try, but software development, the sources are really clear.
You just can't do it that way.
No, that kind of cramming it's impossible. Software cannot be built like that.
Okay, so why? What's the fundamental difference there?
It seems to be about the pace and the mindset required. Software needs this very meticulous, step-by-step approach.
Building the infrastructure piece by piece.
Slowly, methodically. You can't just draw the final picture. You have to write some code, run it, check it.
Do quality control as you go.
Constantly. Ensuring each little bit works before you build on top of it. It needs patience, calmness.
More like building an engine than sketching a facade, maybe?
That's a good analogy. It has to run. It has to be functional at each stage.
Okay, so if you're building it step by step, what does that structure, that infrastructure actually look like inside CAD software? The sources talk about layers.
Yeah, like a hierarchy.
Yeah.
Right at the bottom, you've got the operating system.
Windows, Mac OS, Linux, the basics.
Managing the hardware. Then, just above that, you find the graphics libraries.
Like OpenGL, WebGL, DirectX.
Exactly. And these are crucial for seeing things on screen. Their main job is rasterization.
Turning geometry into pixels.
Right. They handle the visualization, the drawing, but crucially, not the underlying geometry itself.
Okay, so they're like the painters translating instructions into an image.
Then, layered above them is what the sources call the computational geometry layer.
And this is where the core CAD stuff happens for the developer.
Pretty much. It's where you define fundamental concepts, vectors, coordinates, and build the core operations.
Like finding a midpoint or calculating an area. The basic geometric commands.
Exactly. These are the building blocks.
Okay, so that's the pure math and geometry engine. Then on top of that,
You get the parametric design or computational design layer. This is often where designers, maybe technical artists, are working.
using tools like Grasshopper or scripting within Rhino.
Yeah, using and combining those underlying commands built in the lower layers, querying that geometry engine.
And then right at the very top, the bit we all see.
The human-computer interaction layer. the UI UX.
Buttons, menus, viewports, everything you click and drag.
That's the interface.
This layering also brings up that common idea of front end versus back end.
Right, front end is what you see, the UI layer.
Back end is the hidden logic, the algorithms doing the work.
And the sources make a good point here. In graphics software, the back end isn't always a separate server like you'd have in web dev. It can just be those deeper layers. We talked about the computational geometry, the processing algorithms. It's kind of a relative concept within that software stack.
Got it. So building these complex, layered systems, you need structure, right? You can't just throw code together.
Absolutely not. Software development is really about creating structured systems. The sources use terms like pipelines and ontologies.
Meaning structured ways of organizing knowledge and processes.
You take individual algorithms, combine them, scale them up into functions that do more meaningful things together, forming these computational pipelines.
But there's a big warning sign here too, isn't there?
Oh, yeah. Without deliberate structure, it can all turn into...
Empty code.
Exactly. That dreaded mess where everything's tangled. Think of a huge, sprawling grasshopper definition where you can't follow the wires anymore.
It might work, but good luck fixing it or changing it later.
Which raises the key question. How do you keep things organized, especially as software gets bigger?
And that's where design patterns come in. The sources talk about these as like established blueprints for structuring software.
Guidelines to make things more predictable, more maintainable. They specifically highlight MVC.
Model view controller. Okay, let's break that down.
So the model that contains all your core logic, the algorithms, the data structures, the geometry definitions, the calculations.
An engine room again, and it doesn't care how it's displayed.
Exactly. Then the view, that's purely the presentation. The user interface, what you actually see on screen.
It knows how to show the data, but not how to process it.
Right. And the controller is the crucial bit in the middle, the pipeline manager.
The go-between.
Yeah, it takes user input from the view you click a button.
Okay.
It tells the model what calculation to do based on that click. Gets the result back from the model.
And then tells the view, okay, update yourself, show this new result.
Precisely. It manages that whole flow of commands and data.
And the sources really emphasize sticking to these patterns, or at least adapting them consistently.
Yeah, for debugging, for understanding it later, even for yourself 6 months down the line, it gives you a common structure.
A shared language, almost.
And this connects directly to object-oriented programming, OOP.
Which the sources present as a powerful way to build that consistent geometric ontology or hierarchy we touched on earlier.
Right. OOP helps you define things like a vector object with its properties, its coordinates.
Then a point object can be defined using a vector.
And polylines are collections of points, polygons are closed polylines. You build up this hierarchy.
And the benefit is consistency, right? If you define how a point works, anything built using points, like a polyline, automatically inherits that behavior.
It forces a certain consistency and promotes reuse. There's a great practical tip in the sources for academic work, too.
Oh, yeah.
Separating your core geometric logic, the pure math, the algorithms that don't depend on any specific software's drawing functions.
Keep that separate from the code that actually draws stuff on the screen.
Exactly. It makes your fundamental geometric ideas portable. You could potentially plug them into different software environments.
That's smart. Okay, so we've got structure. But performance is obviously huge for CAD. Complex models, graphics.
It has to be fast, or at least feel fast.
Mm-hmm.
Turning geometry into pixels that's handled by the graphics libraries and the GPU, the graphics card.
So optimization is critical. The sources mention a few techniques. One is rendering loop optimization.
Yeah, this is clever. The software doesn't necessarily need to redraw the screen constantly, as fast as it possibly can.
If nothing's changing.
Right, if you're not interacting with it, it can just pause rendering. It only triggers a redraw when you move the mouse, or zoom, or click something.
Saves a lot of processing power without you even noticing when you're actively working.
Exactly. Only do the heavy lifting when necessary. Another technique is object pooling.
Okay, what's that?
Instead of constantly creating new temporary objects and then destroying them, think particles in an effect, or maybe missiles in a game simulation.
The source mentions missiles, right? If they're infinite.
Yeah, hiya now. You'd need infinite objects, infinite memory. Nah, not good.
So pooling.
You pre-allocate a set number of these objects, a pool. When one is needed, you grab it from the pool, use it. When it's done, say the missile goes off screen. Instead of destroying it, you just put it back in the pool, ready to be reused.
Ah, recycling them. prevents memory issues and slowdown.
Exactly. It's used in games a lot, like StarCraft allocating memory for potential units up front.
This also gets into the hardware, doesn't it? The GPU versus the CPU.
Big difference. GPUs are built for parallel processing, doing thousands of small calculations all at the same time.
Perfect for rendering millions of pixels simultaneously.
Totally. CPUs are better at serial processing, doing things one after another, complex sequential tasks.
Like calculating one complex simulation step.
Right. Think of painting a map. A CPU might paint it section by section. A GPU can splash paint across huge areas all at once.
Which is also why GPUs are great for AI training, right? All those parallel matrix calculations.
Exactly the same principle. Massive parallelism.
And then there's shader programming mentioned. That sounds low level.
It is. It's a way to directly program the GPU's parallel processors. You can write small programs, shaders, that define precisely how pixels or vertices get colored or transformed.
Giving you really fine-grained control for complex effects or specific optimizations.
Yeah, you can get significant performance gains for certain tasks by telling the GPU exactly how to use its parallel power.
Okay, so we have the code, the structure, the hardware. But ultimately, software is for people.
And how people interact with it is crucial. The sources wrap up talking about UI UX.
User interface, user experience. We all know the classic interface, WIMP.
Windows, icons, menus, pointers. It's been dominant for decades.
But things are changing. The sources mention post-WIMP interfaces.
Yeah, things like voice control, touch screens, gesture input.
Using depth cameras, maybe, to track your hands in 3D space.
Could be. The ways we talk to the computer are definitely expanding.
And the sources make a really important distinction between UI and UX.
Yes. UI, user interface, is about the visuals, how it looks. The visual design, buttons, layout, aesthetics.
UX, user experience, is broader. It's the overall feeling, how you experience it.
How easy is it to use? How effective is it? Does it actually help you solve your problem well? It's the whole journey.
They use some really memorable examples. The beautiful ketchup bottle.
Gorgeous UI.
But you have to whack it like crazy to get anything out. Terrible UX.
Or that elegant winding staircase, great UI again.
But everyone cuts across the grass, making that worn desire path.
That worn path is the better UX in practice, even with zero UI. People found the more efficient solution.
So aesthetics matter, but practical, effective UX is what makes software truly useful.
Absolutely essential.
And ultimately, the sources kind of bring it all back to this core idea. Software is a system for defining, state, relationships, and rules.
Yeah. How data behaves, how bits of information relate, what happens when you interact with it.
A parametric model is a perfect, simple example of that, isn't it? Defining relationships and rules for geometry.
Exactly. And when you click an icon in your CAD software, you're triggering a whole sequence of those predefined relationships and rules deep down in the system's pipelines.
Input happens, geometry gets processed, the view gets rendered.
It's all orchestrated by those defined rules.
Understanding that how to define state, relationships, rules, how to build those pipelines and structures seems key. Not just for using the tools, but maybe for building the next tools.
So after digging through all this, what does it really mean for you, the listener?
Well, I think it shows that building design software, or even just understanding your tools better, is way more than just learning Python syntax or C++ mech.
It's about architecture, systems thinking.
Really understanding the data, knowing how to leverage the hardware.
And crucially, always thinking about the human using it, their experience, their problems.
How can this tool make their process smoother, better?
And it definitely requires a different kind of patience, doesn't it? That different iterative process compared to traditional design.
Yeah, that whole you can't cram it point really sticks.
You absolutely cannot growl your way through building robust software.
Which brings us to a final thought, something powerful from the sources about value and effort.
They basically say, look, if you want high rewards, you need to become highly valuable. It's simple, really.
And that hitting roadblocks, things not working right away. Gone. No konjaku ge. That's not failure. It's just normal when tackling hard problems.
So considering how complex software development is, how much patience it takes, all the debugging.
How might embracing that difficulty, embracing the inevitable setbacks and failures you'll encounter learning to build these computational tools?
How might that process itself ultimately shape you into a more resilient, more capable, maybe even a rarer and more valuable kind of problem solver within design?
Something to definitely ponder as you continue your own deep dives.